Also, in this case, I like to start with some introductions to the physical and mathematical fluid dynamics and the CFD. And then Navier-Stokes key issues and so on. I will quickly go through this one. So in the fluid dynamics, I think the one needed to understand the Eulerian and the Lagrangian, because they're very important one. Lagrangian means follows the exact motion of that particular particle. So you move with them. But that's a very intuitive, easy to understand. But nonetheless, in the fluid dynamics, that's a problem because there are too many particles. You cannot individually follow fluid motions. And therefore, we have the Eulerian. But still, you can use the Lagrangian in the case of if you found it convenient, like the lava or slowly moving fluid, then you can use it, Lagrangian. But nowadays, because the difference between fluid dynamics and solid mechanics is just convective derivative. So that convective derivative proportional to the magnitude of velocity. So therefore, the Eulerian is the more convenient because instead of following fluid motion, you just stand there and imagine there is control volume, the closed one. It's not actual volume, but imaginary volume. What you do is just count. I'm talking in this subject in my undergrad graduate class, and in Korea, surrounded by sea, we eat a lot of fish. So students can see that much the fish. So under the water, there is control volumes, and the fish will come through the control volume. So you just count of how many fishes comes in, how many fishes going on. By doing so, you can describe fluid motion. How come? Because this. So this is control volumes, imaginary volume. It must be closed. Then it's time derivative. How many? The number of the fishes in total to change with time must be balanced by the outflow and inflow. That's it. That we call conservation laws. Because it's laws. Suddenly fish go to some other universe. Other than that, there must be balance. This is very, very important. All computational fluid dynamics basically based on this. And I mean, if you see Navier-Stokes equation in differential form, it's complicated. But if you look at your fluid dynamics in this way, very simple. You can memorize them. You know what is U is things conserved. The density, momentum, and energy. The momentum is 3 components. In total, 5 equations. With equation of state, it's closed. But in the fundamental level, fluid dynamics is very simple. So this is conserved variable time change of things conserved must balance the function. In this case, time derivative comes in probably in flux across all those surface. So this is volume integral within fish within the volume. This is cross surface integral crossing. It's obvious. That's what we call physical laws. All things, density, momentum, energy must satisfy this rule. Okay, so just remember this is the conservation laws, and we call U as conserved variable, which means there is non-conserved variable. The RMG is all about non-conserved variables. Okay, so I deliberately distinguished the conserved variable and non-conserved variable. Because non-conserved variable can be anything, but though I will focus on non-conserved variable appearing in the conservation law only. I will not consider anything else, which are shear stress and heat flux, the factor. The viscous stress tensile and heat flux vectors. That I will follow. And they are the measurable. You can define from Boltzmann kinetic equations whatever variable you want. You just introduce statistical average, and then you can define it. You put your name on it. No one will care about it, because in many cases they are not measurable. The viscous shear stress, heat flux are also measurable. Measurable means it has some meaning. And this is, so in my lectures, I will use pi. This is viscous shear stress tensor. The Q is heat flux factors. There are only two quantities appearing conservationals. Nothing else. It looks very trivial finding, but very important one. So that means from the kinetic equations, you can derive many other quantities beyond this pi q, but they must not be conceived as equal as this pi q. These things appear conservational. The question is how to define the equation we call constitutive equation to determine pi q. That's it. How to? You can do it experimentally, you can do it empirically, you can based on previous one, but I will do based on Boltzmann kinetic equations. In the case of diatomic case, extended Boltzmann equation. That's it. The same thing in the viscoelastic case. Okay, please remember pi is, I call viscous shear stress, which is tensor. Tensor has 9 components. The 3 diagonal term and the 6 off diagonal term. To me, all the mechanics is what they do is trying to develop accurate method to determine those off diagonal terms. That's it. Is that simple? Don't be confused by other old mathematics. What they try to do is to develop accurate model to describe those off diagonal terms, including the Viscoelastic. So in the college, I think that we have the scalar and the vector, the second length tens, and the third length tens. But in many cases, the mechanics, this is it. That's all you need. So you're better prepared manipulation of the second order tenses. That's it. So you don't need the mathematics beyond that, which will simplify a lot of mathematics, right? So no approximation to so far. So therefore, but this is totally trivial, but the TSMC case, again back to the verification. I mean, I didn't look at very carefully TSMC until maybe 5 or 6 years ago. And, one of my students, Dr. Iranian guy, Karuchani, he was training TSMC. So I was able to talk to him about TSMC. And one morning, how you trust your results? That was my challenge. He said, because it's so good. I'm not satisfied with that kind of response. Because that's the I learned from Professor Rowe, and that's safety. Because the power of those pioneers like Professor Rowe, Anthony Jameson, and Professor Barnier's, they always start from simplifications. I once, because Professor was my supervisor, I once invited him to the erasure. It's hiding.
Yeah.
I think 10 years ago, I invited Professor Rowe to my university and asked the lectures. He didn't bring anything, any slide, anything. Just he said, Roshin, give me chalk. He started from this is true. He started from this equation and then explained beautifully all the essence of the CFD for next 2 hours. So anyway, you don't need it to have very complicated equations. That's what we call modeling capability. That's something every modeler should feel comfortable. Because why we have the model? Because our brain is limited. If you have too many things together, you cannot focus on. But the difficult problems require complete focus. The modeling means that makes you focus on this problem. So identify essence of the problem. So try to do so in many cases, if your own problem. Simplify problem. This is, I think, the simplest equation in fluid dynamics. It's just a advection equation. U is propagate with propagation speed A, because fluid is moving. Solid mechanics, no. That distinction. Okay, so anyway, back to these equations, and then the verification of the DSMC. Oh, I realized that even DSMC, because it starts from like the Boltzmann equation was equivalent of the Boltzmann equation, it must also satisfy this equation. It looks too obvious, but many people say, oh, they thought this equation is not laws. They thought this is Navier-Stokes equation, but this is not Navier-Stokes equation. Because Navier-Stokes equation means you have to prove pi is greater than u. Most of the textbook, they don't distinguish them. So that discussions are turning, oh, why not verify your DSMC solutions using this Navier-Stokes? So that becomes one purpose. By doing so, I will show you later. I mean, you can find a way to improve DSMC, because verification is very, very important. Which means where things goes not accurate. Without that kind of guidance, DSMC, you have molecules, computer take care of all things, and you end up with some final result. And you don't know what's going on. Verification is one way to check it. The making errors, or you identify what kind of error is there. Things like that. So, every textbook, there's equations, but that just a very small point, sometimes very useful. So again, this is conditional. Another one. So in every fluid dynamics text, probably second year, when you taught in the fluid dynamics, I think there's a pi theorem, something like that. Which means you have just several, in particular, momentum equation. And density conservation law, you have only two terms. And the momentum equation, you have several. Then your teachers will tell you that, please derive some non-dimensional parameter. In the many cases, they don't explain why you have to do it. Because there's a name, range number, Mach number, right? So range number and the Mach numbers are the most famous non-dimensional parameter. So you have to memorize it. And then, in particular, experimentalist, you have to worry about that. I mean, wind tunnel cannot satisfy those in-flight range number, Mach number simultaneously, so you have to choose it. Which one you want to abandon. So you live with not accurate range number, and then you have to go through all those corrections, including wall and the infection zone, basically range number corrections. So that sense, this is very important. But not obvious in fluid dynamics textbook. This theorem is you can systematically derive that kind of non-dimensional parameter. It's more like mathematics. But here, what we need is why we care about non-dimensional parameters. To me, it's simple. It's just a comparison of physical effect. In the case of momentum, what kind of effect you have, convectivity, which is distinguished fluid dynamics from solid mechanics, and then pressure, and then viscosity. Because you have three, you want to every given fluid dynamics problem, you need a guideline. Convective term is important or viscosity term is important. You want to have that kind of guideline. That's it. Why we have non-dimensional parameter, every non-dimensional parameter named after very famous physicists like Lagrange, Maher, Lucet, you name it, many. The reason is that's guideline. So in that sense, you don't need this kind of the theorem. Just compare 3-1. I call V I field. The V represents viscosity. I inertia, the P pressure. So if you compare 3-1, you need two non-dimensional parameter. You cannot make order with only one dimensional parameter. You don't know. I mean, first lady, second lady, you compare, and then there's a third lady. You cannot do that. So you need two. So range number is basically I divided by viscosity. So the range number is nothing but comparison of inertia, the most important term in the fluid dynamics, because that makes fluid dynamics move in comparison with the viscosity. That's a range number. So simplification, then you have viscosity, I mean you memorize rho UL divided by eta or mu and so on. On the other hand, Mach number normally in fluid dynamics wasn't defined this way. That's history because Mach defined first time Mach based on speed of sound. The V divided by A. Because of that, everyone said it's Mach number. But to me, you have the another terms left pressure. And the I, because it's what makes fluid dynamics move, you have to use it again. So one time use another term, which means they are the most important one. And you ORF P is left. You have to use it. So I divided P is, it's not M, it's M squared. That's the Mach number. So, but what's the big deal about that? No big deal. This is the same thing. You can try this one. But what is the big deal is, important one is, we have two numbers instead of one. I will discuss about this one because rarefied gas dynamics, it began with rarefaction. If you look at Boltzmann equation, if you ignore the time derivative term, you have only two terms. One is, as I told you, in the microscale level, is the movement and the dissipation. You have only two terms. Therefore, you are left with only one non-dimensional parameter, which is Nusselt number. But remember, Nusselt number is defined by, prefaced by the capital length, there's no velocity. But you cannot think of fluid dynamics that doesn't move, which means there's something missing. So why did that happen? Microscale level, you have movement and the dissipations. Because of that, you have Nusselt number. On the other hand, macroscale level, you have three. Viscosity, very similar to collision, but it's not. And this VIP, because of that, you have two numbers, non-dimensional parameter. So therefore, what that means is, in the macro sense, when you do some experimental work, you need two quantities to classify flow regime you are interested in. That's picture. Which means, I will later explain the misfit. I mean, microfluidics, I mean, many people said only use Nusselt numbers, said Nusselt number 1. But hypersonics, Nusselt number is 0.1. But then you apply Navier-Stokes force. Which one provide a better result? I mean, if you based on just Nusselt number concept, your theory, Navier-Stokes theory for small Nusselt number like the 0.01 must provide accurate results instead of Nusselt number 1 microscale case. But the result is opposite. Navier-Stokes with some select condition many cases, even as high as Nusselt number 1, provide looks like reasonable results. On the other hand, hypersonics, Nusselt number is 0.01. As you know, Navier-Stokes equation is not that good. Why that happen? That can be explained this way. Because Nusselt number is somewhat misguiding. Then what is it? It's the combination of Nusselt number times Mach number. Hypersonics Mach number is 20. Microscale is 0.0001. You multiply by Mach number, even though Nusselt number is 1, degree of non-equilibrium in the case of microscale is smaller than degree of non-equilibrium in hypersonic case. So that kind of things somehow didn't start from many complicated mathematics. Just look back to fluid dynamics taught in the second level, the sophomore of the junior college. Because of that. So it can be range number, Mach number. it can be Nusselt number, Mach number. It can be Nusselt number, like whatever. Two are needed to clarify RMG. So this is, I'm going to emphasize again. Because we have three terms. Then back to the why in the world. Microscopic, you have two terms, macroscale, three terms. The difference is between them, there is a statistical average you introduce. Because of that, velocity comes in. The average velocity comes in because statistical average. That's what I call mesoscale. So, micro, macro, mesoscale. Mesoscale requires average velocity because you introduce some. Therefore, you must keep average velocity in your analysis. You should not do with Nusselt number alone. Nusselt number is nothing to do with average velocity. It's just a thermodynamic quantity. So I think that explains all kinds of those mistakes. Too obvious, but it took several years to figure out this kind of things. I mentioned I went through conceptual revisions because I found some burden. Because I work both. Sometimes that's good things. I mean, rarefied hypersonics is not same as low speed, in many cases, microscales. Because I work together, I was able to see from the top. From the top, then you found some misfit, something bothering you. In order to explain those bothering, I came up with this kind of explain. That kind of thing helps a lot. So, again, this is the integral and the differential forms. Nothing special. Again, and then using Gauss theorem, and then you can have the differential form. Anyway, they are the partial differentiation. Now, with this Navier laws and the Fourier laws, they become Navier-Stokes Fourier. In some cases, you have to put Fourier because with your education, that this is not Navier law. This is Fourier's law. It's about thermal aspect. So we have the mass conservation law, momentum, and energy conservation law. This is realm of thermodynamics, first law of thermodynamics. Energy must be conserved. The why I put some non-dimensional parameter deliberately because M and range number. So this is viscosity, non-conserved value. So range number is high, that this term is negligible, like the Euler case. And then this is, but the RMG is on the other, range number is small. This term becomes important. So that has implication not only in physics but also computations. And then here, convective term, pressure term, you have Mach number. So we need two non-dimensional parameters. So please remember that. So once you solve this equation, then what is final output? The conserved variable rho u p, and also the shear stress and the heat flux. And then derivative can be integrated like this one. Of course, the force also has something to do with normal the stress tensors, like the pi nm. So normally pressure is normal direction, only one, but the viscous stress can also generate normal force. Please don't ignore it. In RMG, that's important. In the first law, Navier-Stokes, many cases, normal viscous stress is small, so you can ignore it. So that means, as I mentioned, fluid dynamics is all about second order tension when you talk about viscosity. So because it depends on there is normal direction, the shear stress. You need to consider both. In the case of RMG, very carefully. So in history, this is the Navier-Stokes. Again, so this is in the case of the two-dimensional system, pi xx, pi xy, yx, pi yy. And then in the case of Navier-Stokes, this becomes the gradient of the u in direction of x, this kind of things. So this is Navier-Stokes. important one is this diagonal term must trace this mean sum of all those diagonal term must be 0. And then non-Newtonian means, the second order means, not necessarily this linear, but somehow let's remove something. Let's say you could have this kind of things. Now Tx is R2. This is nonlinear. Back to the distinction between the linear and the nonlinear geometry. So anyway, this is self-ground defined by Newtonian or Navier in the free law. But we are talking about second order. Okay, another key point. Conceptually, this is also important one. Many people, when I present RMG materials, always they think about turbulence. What happened to turbulence? The answer is there are two extremes. The turbulence is high range number. So high range number is turbulence. The RMG is another thing, low range number. So they don't overlap. That's the conceptual the difference. So you should not mix with turbulence with the RMG. They have different spectrum. But in some case maybe they can overlap, but in general, one is high range number effect, another one is low range. So here's high range numbers, and this is low range. So there were the different reasons. In the case of different turbulence, in the scale of the very small turbulence is not that difficult to understand, like the direct numerical simulation. But the complexity comes in because in fluid dynamics, its degree of freedom is open. Everything, you have open degree of freedom, therefore, few constraints, therefore, higher level of complexity. That's why turbulence is so complicated. The RMG is different. As I mentioned, the kinetic term is all about movement. And then another one is the interactions. But there are two terms interfere with each other. So complexity comes in because of the different reason. Two are very different. The turbulence is very difficult problem, RMG also. But there's a common ground. That if you derive the range average turbulence equation, there's the turbulence tensors. But that is just the second order tensors. Just like the RMG. So if you want to develop the innovative turbulence model, you can start from there. I'm thinking about that direction too. It's all about developing accurate the off diagonal treatment based upon some fundamentals. So that's something the future work I'm looking, just like the Viscoelastic. But the idea comes from that one. So they are a different extreme, but they are also the common one. Okay, what was the key issue? Oh, compressible, incompressible. Some of you from the mechanical engineering, in many cases, mechanical engineering in many cases use the incompressible, but RMG, that's dangerous. Because I think one of the best textbooks I found about distinction between compressible and incompressible is Penton's book. This is viscosity. The viscosity is 1 plus somehow the finite temperature gap, which means if there is a substantial gap in the temperature in the flow domain, it's not negligible. You cannot assume incompressible, even though it makes life easy. It's dangerous. In particular, RMG. But many theories in the particular microgases, people use it in compressible equations, which equivalent to ignores the temperature dependence of viscosity or semiconductivity. That's fatal. I will show you later on. Lot of respects. I understand why people do this, because mathematically once you introduce this become nonlinear equations instead of linear equations. That's it. But physics demanded you have to develop some necessary methods. So that take into account this is rigorous. Otherwise, you are solving incompressible, which is might not be the accurate representation of the phenomena you are interested in. Very, very important concept. In particular, internal flow. Everything is skis. So temperature is very, very important. But nowadays, I think even gas, not much experiment to work from that viewpoint. And another one is, I like to explain the difference between computational physics and the numerical analysis. CFD is broader terms. Everything you're trying to solve fluid dynamics using computer is CFD, but there is two disciplines. One is computational fluid dynamics, physics. Another one is numerical analysis. They are different. In the RMG, what we need is, I think, in many cases, computational physics ahead of numerical analysis. Because computational physics, in many cases, will determine the capability of your numerical method. I have simple examples. I mean, everyone knows what I'm trying to talk about this one. It's quadratic equations. X squared plus 2x equals 3, the same equation. But there are two ways to solve it. One is directly decompose it and solve 1 and minuses. Another one is this is supposed to be 0, 1 minus 1. And then you take this one, you have exact forms. And then you can have, there are different ways to solve the same problem. And theoretically they are same. I mean, as a teacher, I grade this answer is the same, 100 points. But the computation, they are not. Because computation introduces something else. Theoretically, they are the same answers. Numerically, they are different. Here, so sometimes this is better, sometimes this is. So you don't need to come up with a very complicated numerical scheme to make the application. Sometimes you're talking about some new problem like RMG. This is what you can do. Just come up with very simple, different way of thinking. Then sometimes it can make a difference. So just explaining conceptual. The separate process, this is very long, and computational models, Boltzmann, Navier-Stokes, or second order application, geometric modeling, grid, full solution, post-processing, and the validations. Okay, I will run a little bit fast. And this is advection equations. And then this is the partial differential equations. And then using some finite mesh discretizations, del x is cell size, del t times step. Then this equation becomes some system of algebraic equation which can be solved by the computer. During the process, you provide the initial condition in the case of the time accurate equations and the boundary condition. Then you got approximation solution like this one. And then you have to make sure that when initial the size of cell becomes small, they must converge. So that is process. So, but in many cases, something happened because you provide this boundary condition is very critical because aircraft car was different, the shape introduced through boundary condition. So don't forget boundary condition. Your theory beautifully working without boundary condition. Once you introduce boundary condition, it can miserably fail. I look at that kind of things Professor Rose work. He once introduced leapfrog method with the zero disparitions. But it beautifully worked one-dimensional case. It miserably failed two-dimensional case. So anyway, the importance of boundary condition. And then you compare with exact solution that we call verification. This is verification. So this exact solution of this one is But then question is, this is a direction equation, you have this kind of exact solution, and sometimes you don't have exact solution. Navier-Stokes doesn't have rigorous exact solution. That's why we need a computer. How to verify that equation. So there's two things. One is simplified geometry boundary condition. Then you can derive exact solution because geometry is simple. Then compare your solution with that exact solution. That's the easiest way. Or sometimes you can have the manufactured solutions. But in many cases, typically not like that. You just introduce 3 different levels of grid and then check that whether or not your mostly fine grid somehow approached some asymptotics. That's empirical verification. Anyway, whenever you publish your work using CFD, harsh reviews, always ask you, can you believe your result? So you must have your answers. Very, very important one. So this is the basics of the numerical method. Through the Taylor series, you approximate this way, and then this is defined as truncation error. If you remove some high order terms, then message is defined, truncation error vanishes. That's what we call consistency. Which means those discretized versions that follow initial original equations. The consistency and the stability. Then you have freedom to choose time step. You wanted to hurry to get solution as soon as possible, but there's dangers. You work too long distance, your code break down. That's what we call stability. The partial differentiation somehow demand such kind of stability. So I'll skip those next but CFL numbers. Kurang, Friedrich is the supervisor of Professor Grant. Yeah, I guess so. They're famous. Yeah. And so Professor Grant is part-time student. This supervisor realized the talent of the Grant, and then help him pursue the PhD. That's a story I heard from the internet. So anyway, then for given size of the cell size, your time step, whether or not you can do this way. Of course, you can do this work, but that time step is limited due to stability. You have the unstable solution, that's garbage. So you must make sure when truncation errors become small as you increase the grid number, that we call consistency. And the stability, I already explained. If your code, the numerical scheme satisfies both, then we call convergence. So convergence has 2 aspects. One is consistent formulation level and the stability. In many cases, this is difficult because you have some very bad grid and a very difficult boundary condition. In many cases, your code will fail in stability, so you cannot get the solutions. I already mentioned the grid is defined. So you introduce coarse grid and the ordinary grid, you find the grid. Based on that, you can check order of magnitude, which is the accuracy of your code. Typically, NCC fluent and so on is second order, which means you will find 2 times your accuracy level become 2 scale, 4 times more accurate. First order accuracy means you increase 2 times your order of accuracy is 2 times. That's not that efficient. Most of engineering, at least at this moment, most of the cases it should be second order. But if you check NCC fluent for a particular problem, then it's in many cases lower than second order. Why? Because boundary condition. Boundary condition hold on to second order. So 1.7, 1.5, and so on. Then question is decency. Probably decency, probably first order. So therefore, you have to very carefully choose the computational parameter. Make sure that even though it's first order, you put the grid or molecules enough to make sure you're solving multiplication. Very important. So you can check all the accurate of this MC by doing so. This is well-developed practice safely. So you can apply to either MD or this MC, the pure simulation. By doing so, in particular, that's a good subject to the graduate student because they learn limitation of the beautiful MD code that was so advantage. In many cases, they just thought MD is magic, but it's not. You have to look at, you have to learn limitation as well. Not because you, somebody questions your result. In order to improve, you need to know limitation. So this is finite volume method. In my lectures, I will use it often. Again, key point is conjugation rules. There's a control volume, Euler method, you have the time derivative term and the flux. So numerical method exactly following that. So this, remember this. So this is the time derivative of the conserved variable appear here. This is a flux. You are taking count. In the case of the rectangle, you have the four interface. That's it. And in the three-dimensional case, you have the phase. Sometimes you have a cubic, you have 6. So the sigma should be 6 digits. This simplest scheme you can have that because it's based on computational laws. In that sense, it's better than differential forms because remember this is integral form. In the theoretical level, they are the same. But the question is, as I told you, computational physics is different. The integral form, the differential forms are the same. But what you pick up is different. The finite volume method basically pick up integral form. Finite different method pick up in the differential form. But the answer is fluent based on not a finite difference, but finite volume method. I will skip this one. This is just 1D case with VD, and then just the following. And then important of the CFD is always you better prepared to learn something about fluid dynamics first before anything. You try to do it from CFD. And the boundary conditions in particular, they can be slip, non-slip, penetration, pop field. In the case of external flow, means there's the fluid dynamics is funny. You have the flying object, then disturbance generated from those aircraft will go to the infinity. But you cannot solve that way in the computer. You must put or introduce some the code that introduce errors. In many cases, that error is not small, in particular two-dimensional. So let's say I have the cars. This is simple test. I ask my student, solve it. The first thing I check what size you choose computation for. Very carefully it must be chosen. Because that affects the drag coefficient a lot. In particular, to the why? Because there's no third direction to get free. Everyone is skis. So whether or not in the length L, you introduce a 10L or 100L, you will change the drag coefficient a lot. So very carefully. Internal flow, not such a thing. So this is general, but sometimes you don't know this condition, then your computation code must handle that kind of thing. For example, you have airplane, then there's engine sucking the air, but you cannot solve the external flow of the helicopter while you are solving engine flow. Too complicated. You have to cut some air intake, the engine. Then in that coupling you must introduce, but gas must pass. But you have to put in some artificial boundary condition. That case that's not easy. So engineering viewpoint, that all the problem in many cases coming from boundary condition. So be prepared of the many boundary conditions. It is verification and validation. Important one is verification is somehow there is equation. There must be exact solution. Then you have numerical solution. Comparing both. Those two is verification. The validation is not. Validation always compare with nature. They are different. So you have a numerical solution, even though it failed to verify, somehow that solution match well with experiment. That's possible. But that kind of things, I call it garbage, because it's a wrong solution happen to agree well with experiment. That's luck. Next time, luck will not continue. You will miserably fail. So important one is make sure verification, even though it's very harsh. Once you verify, oh, I have to generate this experimental data, your prediction here, I want to make this is close to this one, and then verify it's going down. You worry you want to avoid meeting with your supervisor. That's a natural trend. But don't do that. Just bring that problem to your supervisor. Let your supervisor worry about it instead of you. You agree, right? Yeah. That I call verification. Why? Because validation is experiment is also it has a limitation. Sometimes verification experiment that is wrong. So my suggestion here is, as I told you, always separate what you are doing. First stage, you must focus on qualitative comparison instead of quantitative. Don't try to your prediction dot to dot agree with experimental data. Don't do that. Just qualitative, which means change parameter. The CD is increased or not. That trend is something you're looking at, and it's right, then you feel comfortable. Bring that one to your supervisor, and then with some more computing and then try to quantify. That's a step. And also be aware of always there's some inaccuracy in experimental data, also inaccuracy of computational models. Your model you are using Navier-Stokes equations may not be accurate in the RMG. In that case, you have to question Navier-Stokes equation, not your solution. So that kind of things will be very important to know. If you want to learn about VMV, this is very well-known textbook. But nowadays, very few universities working on new schemes. RMG is a different story because you can use physics, you can use those still, but in many cases, not much interesting in new numerical scheme, but verification because it's important in the company. You hire the PhD from Professor Lakish's groups and assign some problem. And then what the managers want, and the PhD must be able to show BMV so that their result is something designers can use. Very, very important. There are many techniques there. I just introduced the most important one. So I'll skip this one. So again, so focus on qualitative study and then move to the quantifications. And what's also certain computational model, physical models. Your problem is compressible, but somehow you didn't know that because this is a clone that happened to be you use incompressible version of, and then your solution is way off from the experimental data. You wonder whether or not these things and the boundary condition. The answer is you should use compressible code, something like that. There are also all others. Roughness, in particular icing and the small icing dominate micron size, and then stick to the surface. They change surface roughness. They change viscous shear stress, heat flux, and so on. Very, very sensitive. So that case, that's the issues. Okay, so ingredient for validation of computational models, of course, the experimental data, experimental uncertainty propagations. This is one way to identify. Sometimes it's very useful. Others, and so on. Computational errors, and so on. Okay, this is famous. I just brought some of them. Now, I think most important one is it is the poor workman who blame his tools. The good man get on with the job, given what he's got, and get the best answer he can. So that kind of attitude is important. So you are assigned with some new calculation for new design that you found very difficult and then report to your supervisor, say, oh, this is typical, don't do that. I mean, define your problem, and then probably benchmark or simple problems, and then try to generate. During the process, you can identify the problems and so on. And with that, you can talk to boss, and then boss is more experienced. They will give you some guidance, and then next time, you will do better. And but during the process, always work on simple problem first. Instead of the million grid, in the first stage, I recommend you 10,000 grid, because it will give you key access. The check all the things, it's holistic. So whether or not flow looks good, I know that 10,000 is not enough, even though second order mechanical scheme. But if you found boundary conditions working and the coefficient looks good, and then and also qualitative trend, increase angular rotation, whether or not CD increase or not. Then after checking those things, it's time to move to 10 million. And then also always think fluid dynamics before the CFD, and do not trust perfect agreement too much. It's luck. And the wrong solution happen to agree with experimental data. So, in summary, garbage in, garbage out. You provide wrong initial condition, wrong boundary condition, while they looking good, it's garbage. So, the results are only as good as input data. This is true in particular in CFD. Second one, this is again skilled CFD practitioners cleverly use CFD to predict trend rather than guaranteed absolute values. The gap between the predictions, experimental data, trend is good, but there's a consistent gap. There must be some reason. Sometimes you can adjust some adjustable parameter, like the tonus modeling and so on. Okay, this is a famous statement. No one believed the CFD result except the one who performed the calculation. And everyone believed the experimental data except the one who performed the experiment. I mean, this is about 20 years ago, people do this kind of thing. Again, I found it very interesting. Make me laugh. And, this is partly true. Don't, too quickly believe CFD. You have to securitize. Okay, I saw the one is working on LVM, and I'm not that expert in this area, but I found Navier-Stokes versus lattice Boltzmann really change the landscape of CFD. It may create some turbulence in the CFD market. But my impression is it's fun. And it's simple. So always, if you develop some method based upon elementary, very simple logics, but the outcome is beautifully complex and so on, that makes people very surprised. So in that sense, they are successful. But nonetheless, as I told you, sometimes nature demands the complexity. They always issue oversimplification. In particular, introducing particular velocity directions. Yeah. So they will kill compressibility because everything is so tough, tight in that given space. That finest number of velocity cannot handle that. Yeah. It's basic set. So therefore, hypersonics, the compressible, no, I don't think so LVM will replace Navier-Stokes. Because Navier-Stokes, remember, it's based on conservation laws. You introduce control volume, whatever happened there, no problem. That's the power of the conservation laws. Either very high pressure, low pressure, whatever. Okay, this is the end of the lecture. I tried to introduce, because some of you may be not training CFD, but I will heavily use some CFD in the coming lectures. But in the end, you have to solve equations in RNG.